electric circuit.
Bye.
Goes.
Hi. What comes in your mind when you hear the word electricity?
Go.
Energy in the home. Electric circuit. Electricity is important in our daily lives because it is used in lighting, heating, transport, and communication. In our home, there are many appliances that operate on electricity, like gadgets, washing machines, and etc. Of course, the Christmas lights.
Let's begin by looking at how a simple circuit allows a light bulb to light. A circuit is a route through which electrical current can flow. In our example, electrons flow from the negative side of a D-cell battery to a conducting material on the base of the bulb. From there, the electrons flow up a wire that is inside the bulb and across the filament, which is the part of the bulb that actually lights. When the electrons go through the filament, some of the electrical energy is changed to heat and light energy. The electrons continue down another small wire inside the bulb to another conductor on the base of the bulb. The electrons finally make their way to the positive side of the battery. There would not be a complete circuit if the electrons did not travel to the positive side of the battery, and the bulb would not light. When there is an unbroken path on which electrons flow, as in this example, it is called a complete circuit. The unbroken path that the electrons follow is called a closed circuit, because electricity will only flow on an unbroken path. The light bulb will not light unless there is a closed circuit. Now look closely at the light bulb, and you'll notice that there is an insulator between the conductor that leads up to the filament and the conductor that leads away from the filament. Remember that the atoms of conductors easily accept and pass on electrons. The atoms of insulators do not. As we discussed in the first section of the lesson, electrons will not easily pass through insulating material that surrounds a wire. If an insulator did not surround a wire carrying a current, it is possible for the electron flow to get directed to another conductor that comes into contact with the circuit. Electricity will follow the path of least resistance. If the electrons take a path short of the complete circuit, it is called a short circuit.
Go.
Energy in the home. Electric circuit. Electricity is important in our daily lives because it is used in lighting, heating, transport, and communication. In our home, there are many appliances that operate on electricity, like gadgets, washing machines, and etc. Of course, the Christmas lights.
Techno Teaching Info Solution, TTIS presents some essential components of house wiring system. Fuse. An electric fuse is a safety device which is used to limit the current in an electric circuit. The use of a fuse thus safeguards the circuit and the appliance connected in that circuit from being damaged. Refer Figure 16. Switches. A switch is an on-off device for current in a circuit or in an appliance. It is connected in the live wire. Refer Figure 17. Safety precaution. A switch should not be touched with wet hands. This is because water forms a conducting layer between the hand and the live wire of the switch through which the current passes to the hand, and we may get a fatal shock. Earthing. Grounding. First, local earthing. In a house, the local earthing is made near the kilowatt-hour meter. For this purpose, a 2 to 3 meter deep hole is dug in the ground. a thick copper rod which is surrounded with a hollow insulating pipe is put in the hole. The upper end of the copper rod is joined to the earth wire connected with kWh meter. Second, earthing of an appliance. For earthing of an electrical appliance such as refrigerator, toaster, geyser, electric iron, electric cooler, etc., which we handle physically, the earth wire, green or yellow of the cable, is connected to the outer metallic case of the appliance.
Simple electric circuit. A circuit is any arrangement of materials that provides a path for electrons to flow. It consists of a source of electric energy, connecting wires, and the load. The load may be a bulb, a radio, an electric stove, or any combination of these.
Okay, so here we have a simple circuit. In our circuit we have our battery, we have our bulb, and we have our switch. So what we're going to demonstrate right now with this circuit is the function of a switch. So right now we can see that our switch is open and our bulb is not lighting. So what we're going to do is we're going to close the switch and our bulb lights up. And then if we open the switch again, the bulb turns off. So what's happening here is when our switch is open, the circuit is broken. It's not completed. There's a gap in the circuit. Therefore, our bulb cannot light. Whereas when the switch is closed, our bulb does light up. This is because our circuit has been completed. Right, so here now again we have our circuit with our battery, but this time we've got two bulbs in it, okay? So the way these bulbs are arranged is what we call in series. So they're literally going one after the other, okay? Simple circuit, one bulb after the other, in series. What you can see here now is both bulbs are lighting, so it means our circuit is complete, is fully connected. But you may notice that the brightness of the two bulbs is the same for both bulbs, but not as bright as the bulb was in the first circuit we looked at. And this is due to the fact that in a circuit that's in series, these two bulbs, they're getting the same current, so they're getting the same amount of current as the bulb did on its own, but the voltage of the circuit has been split between the two. Okay, so here again we have our circuit containing our battery and again two bulbs. What you'll notice this time though is that the bulbs are not connected in series as in one after the other like we saw in the last circuit. They're connected in what we call in parallel. Okay, so it's one in front of the other. Both the bulbs again are the same brightness. They are much brighter than the bulbs we saw in series. They're pretty much the same brightness as we saw the bulb had in our very first circuit. Okay, and this is due to the fact that the current is split between the two bulbs, but they both get...
Shirley! Sister, can you try to the light? Sorry, I'm studying.
Turning the bulb into load, the electrical energy is likewise converted into other forms like light, motion, and
Current
sound.
and circuit. What is electric current? Let us know about that. We are very much familiar with water current and air current. The flow of water constitutes water current in rivers or canals. The flow of air constitutes air current. Similarly, the flow of electric charge in a conductor is called electric current. For example, let us consider working of a torchlight. Torchlight contains cell or battery, bulb and switch. When switch is on, the cell or battery provides flow of charges or an electric current through the torch bulb to glow. If the switch is off, current does not flow and bulb does not glow. Actually, a switch makes a conducting link between cell and the bulb. A continuous and closed path of an electric current is called an electric circuit. Parts of electric circuit are called electric components. They are bulb, battery, switch and connecting wires. How the electric current is expressed? Electric current is expressed by the amount of charge flowing through a conductor in limit time. Or, we can say that the rate of flow of electric charges. What is the direction of electric current? Actually, in circuits, electrons constitute the flow of charges. But conventionally in an electric circuit, the direction is taken as from positive to negative. If a net charge Q flows through conductor in time t, then the current I is Q by T. The SI unit of electric charge is coulomb. This is nearly equal to charge of 6 into 10 to the power of 18 electrons. We know the charge of an electron is negative charge of 1.6 into 10 to the power of minus 19 coulombs. Measuring of an electric current. The electric current is expressed in ampere, named after the Andre Marie ampere. 1 ampere is constituted by the flow of 1 coulomb of charge per second, that is, small quantities of current are expressed in milliamperes and microamperes. Ammeter is a device which is used to measure the current in a circuit connects in series.
Ohm's law was named after the German physicist George Simon Ohm. This law states that if the physical conditions of a conductor remain same, the current flowing through it is directly proportional to the potential difference applied across its terminals. Let V volt of potential difference be applied across the terminals of a conductor when I ampere current flows through it. Then, according to Ohm's law, V is proportional to I. V is equal to the product of Ri, where R is the constant of proportionality and it is equal to the resistance of the conductor. According to Ohm's law, V is equal to the product of Ri. Thus, R is equal to V upon I. That is, resistance is equal to potential difference upon current. Thus, the resistance of a conductor is the ratio between the potential difference applied across its ends and the current flowing through it. We know that the unit of potential difference is volt, unit of current is ampere, and the unit of resistance is ohm. If by the application of 1 volt potential difference across the terminals of a conductor, 1 ampere current flows through the conductor, then the resistance of the conductor is 1 ohm, that is, 1 ohm is equal to 1 volt upon 1 ampere. Resistances can be combined together in 2 ways. 1. In series and 2. In parallel. First is combination in series, in which the resistances are joined end to end. The total resistance R of the combination in series is equal to the sum of the resistances in the combination. Thus, in the first model, the total resistance R is equal to R1 plus R2. In the second model, R is equal to R1 plus R2 plus R3. And in the third model, R is equal to R1 plus R2 plus R3 plus R4. It must be noted that in series combination, the current flowing through each resistance and through the whole circuit is the same. In case of combination of resistances in parallel, one end of each resistance is joined to one point. Here it is A, and the other end of each resistance is joined to the other point. Here it is B. The reciprocal of the total resistance, R, of the combination in parallel is equal to the sum of the reciprocals of the resistances in the combination. Thus, in the first model, 1 upon R is equal to 1 upon R1 plus 1 upon R2. And in the second model, 1 upon R is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. It must be noted that in parallel combination, the potential difference across each resistance and across the whole combination is the same. When an electric current is passed through a conductor, it gets heated up. This means that electrical energy given to the conductor gets converted into heat energy. This effect is known as heating effect of electric current. Let's perform an experiment to understand heating effect of electric current. Take an insulated copper wire about 1 meter long and wind it completely on a wooden stick. Connect the ends of the wire to a battery and a switch. Now close the switch and allow the current to pass through the wire. After a few minutes, open the switch and touch the wire. You will find that the wire has become hot. This shows that on passing current through a metal wire, it gets heated. Joule, the famous scientist, studied the heating effect of current in detail and found that the heat produced in a conductor due to current passing through it depends on 3 factors. The relation between the amount of heat produced and these 3 factors is known as Joule's law of heating effect of current. According to Joule's law, the amount of heat H produced in a conductor is 1. Directly proportional to the square of the current. 2. Directly proportional to the resistance of the conductor. And 3. Directly proportional to the time during which the current flows. On combining the 3 factors, we get amount of heat produced is equal to I raised to the power of 2 RT. There are many applications of the heating effect of electric current in our household appliances such as electric bulb, electric iron, electric room heater, geyser, etc. An electric bulb consists of a tungsten filament with a coating of thorium. The filament has a very high melting point of about 3300 degrees Celsius and a very high resistance. The coating of thorium provides an extra brightness to the tungsten when it glows. The filament and the entire supporting system are enclosed in a thin glass-made shell. Its filament is supported on thick nickel-iron wires attached to a glass stem. The ends of the filament are connected to contact pins through thick lead wires. An electric bulb converts electric energy into heat and light energy. When current flows through the filament, its temperature rises to about 2500 degrees Celsius and it starts giving light and a little amount of heat. To prevent the tungsten from getting oxidized in the presence of air at high temperature, the bulb is filled with inert gases like nitrogen or argon at a very low pressure. An electric fuse prevents the entire household wiring from getting damaged if a particular appliance draws an excess amount of current. When a large current flows through the circuit, the fuse wire in the electric fuse gets heated up and melts away. In this way, the circuit breaks and hence prevents any damage to the circuit and hence to the appliance. Most of the other electrical appliances such as electric irons, geysers, room heaters, hot plates, ovens, toasters, etc. essentially have heating coils which are made of high resistance wires such as nichrome wires. Nichrome is an alloy of nickel and chromium. It has a very high resistance and can produce large amount of heat. It also has a very high melting point. Nichrome does not get oxidized easily, even at high temperature. The power of an appliance is the electrical energy consumed by it in unit time. That is, power of an appliance is equal to electrical energy consumed upon time taken. In SI system, the unit of electrical energy is joule, J. Unit of time is second, S. And the unit of power is watt, W. So, power in watt is equal to electrical energy in joule upon time in seconds. Thus, if an electrical appliance consumes 1 joule of electrical energy in 1 second, the power of the appliance is 1 watt. That is, 1 watt is equal to 1 joule upon 1 second. Every electrical appliance is marked with its power and the potential difference at which it works. This marking is called rating of the electrical appliance. When an electric bulb is marked 40 watts, 220 volts, it means that if the bulb is connected to a potential difference of 220 volts, the power developed in the bulb is 40 watts. That is, the bulb will consume 40 joules of electrical energy per second. In other words, we can say that this bulb will convert 40 joules of electrical energy into heat and light energy every second. The power of an electrical appliance can be obtained by finding the product of the potential difference applied and the current flowing through it. Thus, power is equal to potential difference into current. Thus, 1 watt is equal to 1 volt into 1 ampere. Electrical energy is generally measured in a unit called BOT, that is, Board of Trade Unit, or kWh, that is, kilowatt hour. 1 kilowatt hour is defined as the amount of energy consumed when an electrical appliance of power 1 kilowatt is used for 1 hour. The energy consumed in our houses, shops, factories, etc. is measured in kilowatt hour. Since power is equal to energy upon time, energy in kilowatt is equal to power in kilowatt into time in hour. Hence, 1 kilowatt hour is equal to 1 kilowatt hour into 1 hour, which is equal to 1000 watt into 60 into 60 seconds, which is equal to 36 lakh joules, that is 3.6 into 10 raised to 6
Smile.
Shara, can you turn on the electric fan? It's so hot.
Oh, yeah. Okay, then. Coming to that.
Thank you, the doctor.
An electric circuit can be opened or closed by turning a switch on or off. When you connect an electric fan to an outlet, you are assembling an electric circuit.
Okay, the problem statement says we're supposed to find the current I1 and the current I2 using the node voltage method. First thing to do is count up how many nodes we have. I see 1, 2, and a total of 3 nodes. There's no indication of which node to use for the reference or the ground node, so I'm just going to go ahead and pick the bottom one. So I'll draw a ground symbol on the bottom one. Next step, assign the node voltages. I'll call that one voltage V1, and I'll call that one voltage V2. After that, we can apply KCL at the remaining nodes. And I'll start on node 1. What I want to do is sum the currents that are exiting that node. So I'll start right here. Current exiting. Well, let's see. 6 amps is pointing in, so it's not matching the direction here. So we'd say we've got minus 6 amps. Coming along to the top, we have 5 amps going with the arrow, so that gives us plus 5 right here. Continuing, we have the voltage across the 8 ohm resistor. So we've got V1 on this side, V2 on that side. So the current going through there is V1 minus V2 over 8. And then similarly, current exiting here is V1 minus voltage on this terminal, which is 0 because it's the ground, divided by 4. So our first equation is the sum of all those values. So we have minus 6 plus 5 plus V1 minus V2 over 8 plus V1 over 4. Sum of that equals 0. Now in the same manner, we can indicate the currents that are exiting on this node, and we have 3, and I'll start again on the current right here. So we have V2 on this side of the resistor, V1 on the other side, so this current is V2 minus V1 over 8. Coming up top, 5 amps is pointing in the opposite direction, so that's minus 5. And then on the bottom current we have V2 on one side of the resistor. This side is 0. And then divide that by 4 to get the current. So at node 2, we sum those currents to get V2 minus V1 over 8 minus 5 plus V2 over 4 equals 0. Now if you solve the pair of equations for V1 and V2 by whatever means is convenient, you should end up with V1 being 8 volts and V2 being 16 volts. I'll go ahead and mark that over here. So now to find the desired currents, on this side we have I1 is 8 volts on one side, 0 volts on the other, divided by 4. Oops, let's try that again. Equals 2 amps. So that would be one answer. And on the other side we've got I2 is 16 volts on one side, 0 on the other, divided by the resistance, and that means I2 is
Factors on which the resistance of a conductor depends. Activity. Take a cell, an ammeter, a nichrome wire of length L and 2L, and copper wire of length L. Procedure. Connect cell, ammeter, plug key with connecting wire in series and leave the gap between the free ends of wires. Complete the circuit with nichrome wire of length L between X and Y. Now plug the key. Note the ammeter reading. Say I1 is equal to 2A. Now complete the circuit with nichrome wire of length 2L. Note the ammeter reading. I2 is equal to 1A. We can say that I1 is greater than I2. We can say that resistance of the conductor depends on the length. Now complete the circuit with thicker nichrome wire of length L. Observe the ammeter reading. Say I3 is equal to 4A. We can say that resistance depends on area of cross section. Now complete the circuit with copper wire of a length L and same thickness equal to nichrome wire. And observe the ammeter reading. Say I4 is equal to 3A. We can say that I4 is greater than I1. We can say that resistance depends on nature of its material. Thus, resistance of a uniform metallic conductor is directly proportional to its length L and inversely proportional to area of cross section A. From 1 and 2 are proportional to L by A. Therefore, R equal to rho into L by A. Here rho is proportionality constant called electric resistivity of the material of the conductor. The SI unit of resistivity is ohm meter. The metals and alloys have low resistivity in the range of 10 to the power of minus 8 ohm meter to 10 to the power of minus 6 ohm meter. For insulators like rubber and glass have resistivity of the order of 10 to the power of 12 ohm meter to 10 to the power of 17 ohm meter. The alloys don't oxidize or burn readily at high temperatures. For this, we can use in heating device like electric iron, toaster, bulb, etc. Whereas copper and aluminium are used for power transmission lines.
First, we're going to say this. The resistance is proportional to the length. That is, if we have a piece of wire, the longer it is, the more electrical resistance there is. And that idea should make sense if you think about it. Imagine trying to force these electrons to flow through the wire. Well, if it takes a certain amount of effort to get them to flow through 1 meter of the wire, then it would take twice as much effort to get them to flow through 2 meters. So the longer the wire is, the more effort it takes to get the electrons to flow through the wire. Another idea is this. The resistance is inversely proportional to the cross-sectional area. So think about the cross-sectional area here, A. In other words, if the wire is really thin, then you're going to have a high resistance. If you have a big number here in the denominator for a big number for the area, which means the wire is really fat, that will give you a smaller resistance. So thick wires have less resistance, and that should make sense too. A good analogy is to think about cars going down the highway. If you add more lanes to the highway, that makes it easier for the traffic to flow. Making a thicker wire is like adding more lanes to the highway. You provide a bigger path, more places for the electrons to go, so there's less resistance. Now we can take those two ideas and combine them. Saying resistance is proportional to L and resistance is proportional to 1 over A, those two ideas together could be written like this. Resistance is proportional to L over A. And saying that the resistance is proportional to this is the same thing as saying that it's equal to some constant times that. So we can say the resistance is equal to some constant times L over A. And if you just write the constant L over A, that means there's some multiplier in here, the constant of proportionality. And we typically don't call it K. We typically use the Greek letter rho for resistivity. And specifically, that's the resistivity of the material. Different materials have a different number right there for resistivity. So we would write the equation like this. The resistance of a wire is equal to rho L over A. So, as we said at the beginning, the resistance depends on the physical characteristics of the wire. So the resistance that you get for a piece of wire depends on how long it is, L, the cross-sectional area, A, and the material, which has a certain resistivity, rho. Now let's think about this equation again. The resistance of a wire, R, is equal to the resistivity times the length divided by the cross-sectional area. Now let's think about the units for a second. Actually, let me move this over here. Okay, think about the units here. Resistance has to be in ohms. Length we know is in meters and area is in meters squared. So the resistivity has to be in ohm meters. And you can see that if you do it that way, these 2 meters up here will cancel out, leaving you with ohms for resistance. So the unit for resistivity is ohm meters. And here's a chart that shows the value of the resistivity for several common materials. Notice for silver and copper and aluminum and also tungsten, but especially silver and copper, these numbers are very, very small numbers. That's 1.59 times 10 to the negative 8th right there. So that's a very, very small number. Glass, 10 to the 9th up to 10 to the 12th. That's somewhere between 1 billion and 1 trillion ohm meters. That's a huge number. And for hard rubber, the value is even bigger, 10 to the 13th up to 10 to the 15th. Those are giant numbers. And that's exactly why electricians typically wear rubber gloves, especially if they're working around high voltage or dangerous amounts of electricity. Because of the high resistivity of the material, it allows very little current to flow, so it provides very good protection. And then look at silicon, right in between. Most materials, as we've said before, have either a very low resistance or a very high resistance, but silicon, the semiconductor, is in between.
This is a review about series and parallel circuits. So there are 2 different types of circuits, series circuits and parallel circuits. In a circuit, the components are joined together by wires. If there are no branches in a circuit, it is a series circuit. However, if there is a branch in the circuit, that means it's a parallel circuit, like this one. More specifically, in a series circuit, there are several components that go one after the other. If you follow the circuit diagram from one side of the battery to the other side, you should pass through all of the different components, one after the other, without any branches. This is how a circuit would be drawn with the components and their corresponding symbols. If you put more lamps into a series circuit, the lamps will be dimmer than before. In a series circuit, if a lamp breaks or if a component is disconnected, the circuit is broken and all the components stop working. Here are some important things to know about series circuits. In a series circuit, the voltage levels can decrease depending on how many components are added to the circuit, but the current will always stay the same. These formulas will also be used to help find the answers to certain word problems involving series circuits. In parallel circuits, different components are connected on different branches of the wire. If you follow the circuit diagram from one side of the battery to the other, you can only pass through all of the different components if you follow all of the branches. In a parallel circuit, if a lamp breaks or if a component is disconnected from one parallel wire, the components on the different branches keep working. And unlike a series circuit, the lamps stay bright if you add more lamps in parallel. Parallel circuits are useful if you want everything to work, even if one component has failed. This is why our homes are wired with parallel circuits. Here are some things to know about parallel circuits. Unlike in series circuits, the voltage levels stay the same throughout. However, the current will decrease throughout the branches. These formulas will also be helpful to find the answers to certain word problems involving parallel circuits.
Connected in series, in parallel, and as well as mixture of both series and parallel. When in a battery, the positive terminal of one cell is connected with the negative terminal of succeeding cell, then the cells are said to be series connected. Here, overall EMF of the battery is algebraic sum of all individual cells connected in series, but overall discharge current of the battery does not exceed the discharge current of individual cells. If E is the overall EMF of the battery combined by n number of cells, and E1, E2, E3 and En are the EMFs of first, second, third and nth cell, then E is equal to E1 plus E2 plus E3 plus up to En. Similarly, if R1, R2, R3 and Rn are the internal resistances of first, second, third and nth cells, then the internal resistance of the battery will be equal to the sum of internal resistance of the individual cells. That means R equals R1 plus R2 plus R3 plus up to Rn. When positive terminal of all cells are connected together and similarly negative terminals of all the cells are connected together in a battery, then the cells are said to be connected in parallel. If EMF of each cell is identical, then the EMF of the battery combined by n number of cells connected in parallel is equal to EMF of each cell. The resultant internal resistance of the group is the parallel combination of internal resistance of all individual batteries. The current delivered by the battery is sum of currents delivered by individual cells. Now let's have a discussion on mixed grouping of battery cells. As we said earlier, the cells in a battery can also be connected in mixture of both series and parallel. A load can require both voltage and current more than that of an individual battery cell. For achieving the required load voltage, the desired numbers of battery cells can be combined in series, and for achieving the required load current, desired number of these series combinations are connected in parallel. Let m number of series, each containing n number of identical cells, are connected in parallel. Again, assume EMF of each cell is E and internal resistance of each cell is R. As n number of cells are connected in each series, the EMF of each series as well as the battery will be N into E. The equivalent resistance of the series is N into R. As m number of series connected in parallel, the equivalent internal resistance of the battery is N into R divided by M.
Go.
Okay, in this activity, I will show to you the arrangement of a series connection. You will need the following in this activity. 2 bulb holders, 1 dry cell, and connecting wires, and metal connectors. Okay. John Mark Matbagon Nakugmata will demo the how to arrange the series.
Thank you, GP Dakogulo. First, I will show you how to make the series connection. First, get the dry cell and put it to the metal connector. Metal connector. No, it's the bulb holder. Bulb.
Oh, it's jumping, it's living.
Oh,
Living things.
swallowing. Metal connector.
Metal connector.
And bulb holder. Ito ang series na.
Ikaw.